Next problem. Consider the random process x of t is equal to y cos omega t greater than or equal to 0, where omega is a constant and y is a uniform variable over 0, 1. Find the autocorrelation function Rxx of t, s of x of t and autovariance, that is covariance, Cxx of t, s of x of t. We'll see the solution. X of t given, it is equal to y cos omega t, that is 1, equation number 1. Also, y is a uniform variable over the interval 0, 1. We know the PDF of a uniform distribution, right? 1 by 1 minus 0 if 0 less than y less than 1, 0 otherwise. If it is lies between a and b, if theta is lies between a and b, then the uniform distribution PDF is given by 1 by b minus a, where theta lies between a and b, 0 otherwise. So here we are using the same thing. Here b is equal to 1, a is equal to 0. So you will get 1 if 0 less than y less than 1, 0 otherwise. Now find the autocorrelation of x. So we know Rxx of t, s, which is equal to expected value of x of t, x of s. So from 1 we know the value of x of t, y cos omega t, then y cos omega s, right? It is e y square cos omega t cos omega s. We are taking outside from the expected values, because y is the only random process, that is variable. Y is a uniform variable they have given. So that is why expectation apply only for the variables. So expected value of y square cos omega t cos omega s are constants we are taking outside. So that is equal to integral 0 to 1 y square f of y dy. Because we know expected value of x for a continuous distribution, the interval is given with the PDF f of y, that is equation number 2, 0 to 1, that x then f of y dy, that is the rule. So here instead of expected value of x means x into f of y dy, y means y into f of y dy. So whatever the expected value, so you can bring it the integral 0 to 1 y square f of y dy, right? That is the definition of expectation, into cos omega t cos omega s, which is equal to integral 0 to 1 y square, because we know 0 in the interval 0 to 1, the value of f of y is 1, y square dy cos omega t cos omega s. So integrating y square, you will get y cube by 3, lower limit 0, upper limit 1, cos omega t cos omega s. So applying lower limit and upper limit, you will get 1 by 3 cos omega t cos omega s. That is equation number 3. Now need to find auto covariance. That is autovariance or covariance, both are same. Cxx of t, s. We know the formula Cxx of t, s, which is equal to Rxx of t, x minus expected value of x of t into expected value of x of s. So we know the autocorrelation of x, that is equal to 1 by 3 cos omega t cos omega s from equation number 3. From equation number 1, we know the value of x of t and x of s. So expected value of y cos omega t into expected value of y cos omega s, that is equal to 1 by 2 cos omega t cos omega s minus cos omega t is a constant, cos omega s is also a constant, taking outside from the expectation, cos omega t into expected value of y into cos omega s expected value of y. So 1 by 3 cos omega t cos omega s minus cos omega t into cos omega s expected value of y 2 times, so e of y the whole square, that is equation number 4. Now we want the value of expected value of y, e of y, which is equal to, from the definition, 0 to 1 y f of y dy. 0 to 1 integral 0 to 1 y f of y is 1 by equation number 2 into dy. So integrating y, So you will get y square by 2, lower limit 0, upper limit 1. So substituting the lower and upper limits, you will get 1 by 2, that is equation number 5. So use this value in equation number 4. Therefore, the covariance Cxx of t, s, which is equal to 1 by 3 cos omega t cos omega s minus 1 cos omega t cos omega s into 1 by 2 ey square. So 1 by 2 square. So you will get 1 by 3 cos omega t cos omega s minus 1 by 4 cos omega t cos omega s. Taking LCM 12. So you will get 4 minus 3 1 cos omega t cos omega s. That's all. Thanks.